Okay, so this is session 6. We just wrapped up a pretty intense session on inverter-based resources, and we're about to move into our resource adequacy session. We have another great lineup of speakers, another great panel scheduled, and this one is going to be chaired by Tom Acker, previously with Northern Arizona University, and now with, let's see, I got to get it right. I'll make sure you're with Salt River Project, Arizona Public Service, or Tucson Gas and Electric, right? One of these places down here, Salt River Project. Okay, so Tom is a longtime member of ESIG, good friend, and I'm going to turn the session over to him. So, Tom, it's all yours.
Thank you, Charlie. So when I started coming to these meetings, it was the Utility Wind Interest Group, wind being the key at the time, and turns out I went to this conference and there was a wind turbine at the conference and there was a solar panel too. And the wind turbine leaned over to the solar panel and said, "Hey, I'm a big fan." A little closer, thank you. So it has been quite the winter. I live in Flagstaff. It's about 4.5 hours north of here. And this year we're at 7,000 feet. We've had over 15 feet of snow in town. So it's been a great winter. It's been cold too. My wife got me a sweater, and the sweater, however, has been picking up a lot of static electricity. And so I took it back to the store and they gave me another one free of charge. Okay, so good morning to everybody. So as Charlie mentioned, my name's Tom Acker. I'm from Salt River Project up in Phoenix. SRP is a large public power, water, and electric utility in Phoenix. And our mission is to provide sustainable, reliable, and affordable power to our customers. We have about 2 million customers. At present, we have about an 8,000 megawatt peak load. We've got about 400 megawatts of renewables. Most of that is solar. But things are changing, and we are currently putting in the ground 2,000 additional megawatts of solar, some wind, and we're working on putting in 800 megawatts of battery energy storage over the next couple of years. So all that stuff's in process. We have some aggressive decarbonization goals, like many of the utilities and RTOs across the United States and the world. And so when we get to 2035, we expect to have 2/3 of our energy generated from renewables. We expect a growth in load of about 1/3. So we see about 10,000 megawatts or more of renewables on our system. Right now we have an 8,000 megawatt peak load. That's a huge change. There's big changes coming. We have a lot of things to consider as we transform our system into that low carbon and eventually no carbon system. So one of the top questions on our list is about resource adequacy. How do we actually determine what our resource adequacy is? And that, if you haven't seen it, there's a very nice ESIG report. Let me read you the title of it. It is Redefining Resource Adequacy for Modern Power Systems. It's on the ESIG website, and there's also a fact sheet to go with it. It's worth a look if you're interested in this and you haven't seen it. But that really sets the context for today's session. And we've got 5 excellent speakers today. And we're going to cover a range of topics, starting from climate and weather impacts on resource adequacy and taking it to markets, and there are evolving markets throughout the world. And so our first speaker is going to be Justin Sharp. What we're going to do is we're going to proceed through our 5 15-minute presentations, and we're not going to do any of the clarification questions. So we're going to go straight through these. That should give us about 25 minutes for Q&A at the end. So with that, I'd like to introduce our first speaker. Justin Sharp is principal and owner of Sharply Focused LLC, a consultancy specializing in the intersection of atmospheric sciences and the electric utility sector. Justin began work in the utility business in 2004 at BPA, moved to PPM Energy, now Avangrid, in 2005, where he built and directed Avangrid's renewable energy meteorological forecasting and operational analysis function from the ground up, including the first 24/7 wind energy forecasting group for operations and trading. Sharply Focused was founded in 2012 with the objective of helping clients utilize weather and climate intelligence in the utility sector with a view to furthering the energy transition. So with that, turn it over to Justin.
Thank you for that introduction, Tom, and thank you to ESIG for inviting me to speak today. So I'm going to sort of kick things off by looking at basically the underpinnings of a lot of the resource adequacy work that we have to do. Basically, we're transitioning to a weather-dependent system, and so a lot of what is underpinning future analysis is weather data. And I'm immediately hitting technical difficulties. Shoot. Oh, there we go. So we're in the midst of an energy transition. We're decarbonizing by electrifying almost everything to basically generate with zero carbon emissions. We're going from our current system, which is largely fossil-based, over to a largely renewable system. And this is kind of me trying to bridge the gap after I've had dinner at ESIG. I don't have any other jokes. Tom was the provider of the jokes, except I can give you a weather forecast maybe. Anyway, radical change is needed, and I've always been a believer that we can't shoehorn renewables into the existing system. The existing system was designed for dispatchable generation. We have to fundamentally change the paradigm. The electric system is full of uncertainty as it changes radically. Loads are going to evolve dramatically with the deep decarbonization. The economics and policy are now driving ever larger renewable energy shares, which is great for humanity, but we have to keep the lights on and we need to keep sight of that. And I thought Alice did a great job on the first day, sort of bringing that out. We also have a lot of uncertainty around the future resource mixes. But what we do know about is weather and current climate. And we actually can provide a fair amount of information about that, but with a fair amount of caveats too, unfortunately. Anyway, this is my picture of the meteorologist who I feel is now to renewable power as the geologist was to oil and gas. So we must enable better decision-making, especially for planning horizons with the variables that we do know a lot about. And that involves procuring and creating the right data for power systems modeling and using it appropriately. And then working together to build better system models too. And with that knowledge, we can deploy storage and we can strategically place generation to minimize risk, assuming we can get regulatory and political buy-in. Anyway, the impact of weather and the definition of extreme weather is also shifting right now. We think of extreme weather as being like snowstorms and cold waves and things like that. And what will be extreme to the system will be different going forward into the future. Temperature will still obviously be an important driver, but what's happening with renewables will be really important too. And I'll show that in a second. And Josh Novarchuk and I and some other folks at NREL did a report on this a couple of years ago, which is a reference to. So this is what our new system looks like. So basically on the far sides of this plot, we have now 2022. This side is demand, this side is generation. And what I'm trying to show here is how the weather dependence increases over time and how the weather complexity increases over time too. So these blue arrows represent weather dependency and the red arrow represents weather complexity. And you can see the complexity increases for demand. The dependency increases a lot as we electrify HVAC. That's largely a temperature dependency on the generations. And then in addition, we have a dependency here from transportation. Our electric vehicles are essentially small residences on wheels. And so they are impacted by temperature as well. People use more energy when they drive during the morning, on a cold morning, or on a hot afternoon. On the generation side, you can see that fossil should drop to zero, assuming we manage to do that. We've got bigger problems if we don't. nuclear stays about the same, hydro stays about the same, and wind and solar pick all that up, which means that we're going from this moderate weather dependence on generation right now, where temperature has this small impact on the current fleet. And then we've got the existing renewables, to a large dependency where solar is dependent on aerosols and clouds, and then some dependency on temperature, and also things like snowfall and ice. And then wind has obviously got a large dependency on the wind in the atmosphere, and also temperature and humidity. So this is a picture showing those interactions in more detail, and I've decided not to go through it because I don't have time, but in a nutshell, there is a lot more complexity. This is a slide that just shows some of the results from the work that Josh and I did, which basically, what I'm trying to show here is that weather is becoming a predominant driver of both supply and demand balance. The risk shifts from peak demand, which was driven by temperature, to peak demand net of renewables, which is driven by temperature, wind, and solar. And most of the time, the system will have wider margins and will become oversupplied as the penetration increases, but high demand with low renewable resources will become as impactful and ultimately more impactful than peak demand. And what you can see here is it's a hypothetical system based on NREL's NARIS work. And what I've got here is net load plotted against load. And this is 2024, very similar to now, very tight spread. So the color here represents the probability density, very tight spread of load against net load with just some small variability due to renewables. And then as you get to 2036 with a lot more renewables, you get a lot more diversity. And in 2050, you've got a lot of diffusion. And you can see a few things. This is just annual hourly net load versus load. You can see a few things here. You can see the day and night time effect of solar. You can see days that are sunny, clear days where net load is lower than load. You can see the seasonal variability. This is largely the impact of seasonal variability on solar. And you can see an oversupply right here where our net load has dropped below zero. And up here where I put the exclamation points, this is the area where load and net load are basically the same. In other words, we don't have any renewables. And this actually extends a little bit above my circle here. And so there are times when there are almost no renewables on the system. And we have to bear that in mind. A lot of people are like thinking that this doesn't happen. It does happen. The sky is not falling down. We can deal with it, but it does happen. So this is an illustrative example. I am not a power systems modeler, so this is by no means perfect. An illustrative example of how weather is incorporated into power systems modeling today. Basically, you often start with a time series, a load time series, you normalize that, and then you create a temperature versus load function, which is an example is given right here. So you can see in the wintertime where people are using more electric heat, during cold waves, the demand goes up, and then in the summertime, obviously, it goes up a lot as people start using more air conditioning at higher temperatures. That then gets used to calculate long load time series, and then you can play games with Monte Carlo where you basically go through a bunch of different scenarios using random draws, because essentially the hydro and the outages and the load are somewhat decoupled. They're not exactly decoupled, but they're generally considered as fairly independent. Now, where we're going is to a situation where we now have load, wind, and solar all dependent on weather and all dependent on the same weather at the same time. And that creates a much more complex system with a lot of dependencies where you can't play those same Monte Carlo games anymore, because you have these multidimensional probability spaces where everything depends on everything else, and it depends on what happened in the previous hours as well. So this is just an example of some of that complexity in the temperature field, the wind speed field, and the solar field. And then there's some wind projects that are plotted on this, and I'm sorry, you can't really see this very well. But the idea is to show you that there's so much complexity going on in any given moment, and it all depends on each other. It all interacts. What we need to do for power systems modeling, particularly for resource adequacy analysis, is is we need to be able to estimate the renewable generation at an appropriate aggregation level for the same pattern that's driving load. And we need to do it chronologically. The reason we have to do it chronologically is because we have storage. And so if you have a sunny period, you obviously want to store that energy if you're oversupplied. And then when you have a period where there's low renewables, you want to be able to pull back from that. So there's two approaches to do that. One is bottom up, which is to produce a reasonable estimation of the generation at every possible location for wind and solar, and then aggregate to the required level. And you can do that for different portfolios, including ones that don't exist yet. But that requires very detailed data that is carefully validated and shown to be accurate. And then the other method would be top down, which is typically how operational forecasting is done today, where you create a model that relates the existing generation to weather data sets and usually use machine learning to figure out how much generation do I get for a particular weather regime that my weather model is telling me. That's much easier to implement, but for the purposes of power systems analysis, it's hard to implement it accurately due to the lack of power data. And it requires extrapolation of existing generation to new plants that don't exist yet, where we don't have any data. So what I would posit is that the bottom-up approach is really the only viable approach right now. Some people might disagree with that, but that's an ongoing conversation. So quick audience participation time, and I see I'm running out of time, so I got to go quickly. First of all, before I ask the first question, how many meteorologists are in the room? 2. Okay, good to know. You guys keep your hands down. How many people in the room have conducted power systems modeling studies or used the outcomes of the decisions in their work? Have a quick show of hands. So about 50%. Okay. How many know where the weather inputs that are used for those models have come from? Probably about 2/3 of those folks. Good. And how many have validated the accuracy of that weather data that underpins their studies? Okay, so I think you take the point that I was trying to make there. It's good that some people have. That's actually quite reassuring to me. And then how many have looked specifically at the accuracy during low resource periods? 2 or 3, okay. Okay, so I have a radical hypothesis. The historical generation estimates that you're using for power systems modeling are currently less accurate than those that are coming out of operational generation forecasts. I don't know how big of a surprise that's going to be to some people. I'm suspecting it's a surprise to some people. I think this is true. I'm not saying I guarantee it's true. I can't absolutely prove it yet, but I hope to at some point. And the big reason for that is because the plant data isn't available for training and validation of the power systems modeling data, while it is available for operational forecasts. And partly it's because more attention's been paid to operational forecasting right now. So I'm going to make a bit of a change and put my conclusions up front before I go through a couple more slides. I think we're in collective denial. The data that we have is not sufficient for the task that's at hand. And if you put garbage into a model, you'll get garbage out. Now, I'm not saying the sky is falling down, but I'm saying there are problems. We can create a better data set. And I love this Dilbert cartoon, by the way. I'm not going to go through it, but I think we've all had this at some point in our lives. Creating a better data set is possible. It's not trivial, but the cost will be very small compared with the trillions of dollars we're spending on the energy transition. And industry collaboration and cooperation is absolutely essential and the low-hanging fruit. And this data that I showed you before came from some data sets that I'm going to talk about in a moment that I think are part of that collective denial. I've done it too. So you're not alone in that. So now I've got your attention. Here are the challenges. The weather input validation and statistical correction is difficult to impossible because we don't have any data, right? That's where the industry collaboration comes in. Meteorological data is being used as a black box resource with the assumption of observation level quality. So that data that you're using, it's not observations, right? Even ERA 5, it's not that, it's coming from a model. It's model data, and it has errors and uncertainties that are significantly higher than those of observations. And meteorologists are not questioning how power systems practitioners are utilizing this data. They're just handing it off, and they're actually trying to make it easier for people to just take that data without consulting a meteorologist, which I find problematic. And the lack of validation is a real problem too. There are silos absolutely everywhere. I need to move forward fairly quickly here. So blow up the silos is my message there. So I got a couple of examples to show this. The first one is the data that we're using right now typically does not have sufficient resolution. The data here that's on the right-hand side, these are for exactly the same domain. They're the wind speed, they're the same domain, same time. And one of them's from a very high resolution model that we were using at Iberdrola Renewables. The other one's from ERA5, which is one of the most commonly used data sets for power systems modeling. You can see there is a ton of structure in here that is not represented in here. If you don't capture these structures, which you can see animated here, and by the way, these points here, the blue points are the mirror data points, and the green points are the ERA5 data points. If you can't capture this structure, you can't capture the variability in the wind field, and you can't capture some of the phenomena that are occurring. Example 2, validation. This is a validation I did for GridLab for Bonneville for a project that they were doing, where I was looking at how well is the wind generation in the Bonneville Power Balancing Authority predicted by the wind toolkit from NREL. And what I found was that in the wintertime, we have a significant high bias from the model, up to about 10% in December. Overall, annually, there's a high bias, but in the winter months, December, January, February, very significant high bias. And that is due to a well-known problem with numerical weather prediction. On specific days, those estimates can be up to 23% in error from a capacity factor point of view. That's raw capacity factor. So the model could say, I've got 26%, and the reality is you've got 3%. From a resource adequacy point of view, I hope you can see that's a big problem. Another example, just to show that's not just in terrain and in an area where I did my PhD on, this is Texas. This is some work that was done by one of our presenters yesterday, actually, that shows the level of error at all the wind farms in ERCOT, 100 wind farms. And this is root mean squared error. You can't see the numbers very well, but again, we're in the 20% error range here. This is binned by the actual capacity. So I'm interested in the area where capacity is predicted to be very low, where the actual capacity was very low. And the errors are actually up to 20%. Now, you can't predict negative capacity, so those errors are 20% positive, which again is a problem. And then, because I don't have much time, NSRDB also, I think, can potentially have some issues from the perspective of errors for power systems modeling. So my takeaways are that, as I said, the data is insufficient for the task at hand. We're basically flying blind. Creating better data is possible, but the limitations, it's never going to be perfect, and the limitations must be understood. It must be produced on an ongoing basis, so it's future-proofed. It must be validated. It must be transparent and openly available, and the uncertainty needs to be clearly communicated. And the industry collaboration here is really low-hanging fruit. I went and did a poll last week, a couple of weeks ago again, to try and get data from generators. They told me there is no way you will ever get our meteorological data, and definitely no way you will get our generation data. That's got to change, because otherwise it just doesn't make sense. It's a tragedy of the commons, basically. And then engineers and meteorologists need to work together. So that's the end. I'm not going to go through this table. This table is a quick summary of where we're at. Where we're in green, these are data sets that do where there's green, the data set's doing quite well. Where there's red, the data set's doing really badly. I know you can't read this, but the bottom line is there's not a lot of dark green on here, and there's a fair amount of dark red. So there's room for improvement. More details on this are coming soon in a report that a task force is producing for ESIG called the Weather Systems Inputs for Power System Modeling. So stay tuned for that. That's it. Thank you. Sorry for going a little over, Tom.
Thank you, Justin. So our next speaker is Sean Morash. He is a principal at Telos Energy, where he helps clients with the energy transition by applying novel planning techniques to new challenges. Prior to joining Telos, Sean was a consultant with Internet's smart grid team. Outside of work, he's an adventurous and a self-described baseball nerd. Might throw a ball out to you guys today. His topic is probabilistic operational strategy with increasing solar and storage.
Thank you. Mic check here and see if this works well. Thank you for the intro, Tom. I'm Sean Morash with Telos. When I said that to somebody yesterday, they kind of squinted at me. And I had to clarify that I'm not Derek or Matt. I am Sean. I was used to that. I was with Internex and the same thing happened, but with Bob Zavadil instead of Sean Morash. So thank you to eSig for having me up here. And I'm going to chat through a little bit of some work that was done and introduce a different topic here on, related to resource adequacy, but kind of more around the operational components of this. So I'm going to introduce a framework for evaluating kind of power system operational strategies. This is, really, we're getting more and more into trying to shoehorn operational techniques and realities into resource adequacy, more and more uncertainty into our resource adequacy analysis. There's more uncertainty than even what's being represented in our kind of resource adequacy working groups. I'm going to work through a sampling of results kind of on a project that we did, but I really want to orient and focus on the kind of framework and the modeling, like what's possible. So I want to talk through kind of, we've got different stages. I'm going to work through this quickly. We've got our capacity expansion planning, which answers the question of, what should we build? What should we retire? We've got our resource adequacy analysis, helps us answer the question of, all right, is that portfolio reliable across a number of uncertainties, across the different weather years, across different, things that can happen. I want to talk about kind of, okay, we've got a portfolio that we think is reliable. How do we operate that, right? How do we reliably operate a portfolio of new resources that we haven't operated before? And then there's basically this morning's conversation of analysis that's required around, okay, what are the electrical engineering constraints, right? And you can think about these in kind of a time series step, right? We go from a kind of annual look or whatever into an hourly look, and then we can do maybe minute by minute orientation, and then kind of, into seconds and cycles. Ultimately, right, what I'm trying to get to is from an operator perspective, if we've got an already complex system, we're throwing a bunch of wind, solar, and batteries on it. We're also retiring a bunch of thermal resources, changing customer dynamics, basically everything we've been talking about. How do we operate that? What's our reserve strategy? How do we make our unit commitment decisions? So when you ask that question, all right, what's our requirements for a model that'll answer those questions? All right, we know we want something probabilistic. We know we want something that looks at every hour of the year, right? There's different challenges that pop up with different weather patterns. Hey, maybe your maintenance schedule needs to be rethought. Maybe that's not quite, the way that it should be. But we also know we need to introduce weather variability. We need to, I don't need to go over that again, but we also need to introduce, forecasting accuracy, right? How do I prepare a reliable system knowing that my day-ahead forecasts are going to be wrong? And we know we need to orient around unit commitment decisions, right? So I've characterized traditional approaches here, but the other kind of thing that I didn't quite characterize, right, is the operational experience of operators, right? Well, hey, we do these things because of X, Y, and Z, and it kind of has built up this systemic knowledge over time. Those get eroded with new portfolios. So modeling that I'm talking about really orients around setting up things in day ahead, and then introducing a little bit of chaos, a little bit of uncertainty, whether that's forced outages, weather forecast errors that affect your generation side, load forecast errors that affect your demand side. And so I've got some things here. I think most of the folks in the room here would be able to understand what's going on, right? But we're talking about in our day ahead, things are, we're able to procure enough resources, we're able to have, life is good, basically. We've got a good plan, and then everybody's got a good plan until they get punched in the face, right? So we've got our forced outages that can crop up in different areas. We've got our forecast errors that can crop up, and all of a sudden you find yourself in a bind. So the way that we went after this, our friends at Analytics PSO have this fun decision cycle framework. They've got some resource adequacy work that they've been doing under this ARPA-E effort it's called SNAP. But this framework was helpful for me in characterizing the difference between what I'm kind of talking about, which is the reserve policy analysis, right? That happens in between your kind of intraday scheduling and your real-time dispatch, versus resource adequacy analysis, which is looking on a day-by-day basis. Am I good in my day ahead plan, right? Do I have enough resources? When we got started with this work, I was really nervous that the answer that I was going to come up with was challenging the resource adequacy work, right? Hey, I can't figure out how to operate that portfolio. Turns out that it's not as reliable as we thought, right? Our metrics are a little different. We need to rethink our resource portfolio. So what did we do? We set up this, this is going to get worse too before it gets better. We set up this modeling approach where we've got our kind of day ahead plan that has a time horizon, right? So you've got your plan for the day and you plan for the rest of the week. And then that's feeds into a real-time cycle, which solves every hour, right? But it also looks ahead 6 hours, 8 hours, whatever, to make sure that you're prepared for, system peaks. You're not spending all of your energy storage right away. Whenever something pops up, you're making your unit commitment decisions around, making sure you're good for the rest of the day. So we've got our framework. That's cool. And then I wanted to I could spend probably an hour explaining all of this, but basically your forced outages show up in different ways, right? They can show up and surprise you. They can kind of disappear within a day. They can show up and affect your next day ahead and kind of, cascade into different challenges. There's a lot of work that was done to ensure your forced outages kind of showed up when an operator would actually see them, and that the model didn't have too much foresight into what was going on. So let's get into a couple of results here. So we took a look at a real system, real balancing area, wanted to backcast what was going on. And so we did so, right? So we've got our kind of historical operating strategy, got our historical system. There's a lot of green on that slide, right? So, man, things are pretty reliable. That's good. We've got a model that represents sort of the system as we know it. You'll see a little bit of discrepancy in terms of, the model, the backcast model has this, 0.21 shortage hours. Historically, there's like 11 a year. And that really comes back to our definition of shortage hours, right? So when we first got going with this project, we were using terms like LOLE and unserved energy. And that was problematic, right? Because we were doing something a little different than that resource adequacy work. We were doing kind of intraday modeling. And so I'm going to orient around shortage hours as kind of hey, we're in a pinch, what do we need to do? So the definition of short drives a lot of the discrepancy here. And it turns out the more digging we did, it was kind of some operational practices were not entirely consistent across different kind of, I don't know how to say it. Not all the operating groups used the same playbook. There was a lot of flexibility within the operating practice, right? That was kind of intentional. Some folks leaned more heavily on the reserve sharing group than maybe the model would have, right? So what happens if we apply our historical operating strategy, our historical reserve strategy to a different resource portfolio? A lot of our green disappeared. So we've got a bunch of shortage hours that creep up here, kind of when overnight, right? So in our non-solar hours. So we've, the particularly interesting finding here, right, is all right, every month across the kind of x-axis, and then our y-axis is both hours on the left and then kind of hours on the right. But we can see, hey, at hour ending 23 or hour of the day 23, it's 11 p.m. That's when we have our biggest problem, right? That's not our historical biggest problem, but comes back to our kind of solar and storage plan, right? So we can zoom in a little bit more on that and say, all right, who's helping and hurting, right? When we're having these shortage conditions, which resources are contributing, right? And so I quickly, you kind of work through this. All right, coal, that's lower than I would have thought. Well, maybe we got into the shortage situation in the first place because our coal tripped offline, right? Same story with combined cycle. All right, cool, hydro's helping, quick start peakers are helping, solar is not really helping, but you remember we were experiencing most of our shortage hours when, it was overnight. But man, our storage is not doing what we think it should do, right? We've got this super flexible resource. We should probably get it to respond, right? So we got to come up with a new strategy for that storage. So work through a bunch of scenarios, a bunch of analysis, a bunch of settings, kind of trying to think through how do we get our storage to operate reliably in the face of all of this uncertainty. So, hey, we've got that same portfolio, but with a different operating practice, got a whole bunch better reliability, right? We've got a bunch more green on here. That's what we're looking for. So, this boils down to how and when storage was dispatched. So we had a bunch of kind of ideas here. There's a strategic hourly storage target, right? So, hey, storage, make sure you're fully charged going into the peak. Even if you think you can get away with it because it's a little, sunnier than we forecast, or whatever. We need to kind of adjust our reserves hierarchy a little bit, right? So the other way to say this is, hey, we really need to ensure our storage is charged enough so that we meet system peak. The best way to do that is to, if we experience something in the middle of the day that we can handle with other resources, go ahead and handle with the other resources and make sure our storage gets charged up. The other thing I was going to mention on this slide, you'll see, hey, we're not quite to the historical context of short hours, right? 26 versus, the 11 historical context. A lot of these shortage hours come back to kind of minimally problematic space. So I didn't characterize it on this slide, but a lot of these shortage hours, you're like a couple of megawatts short, right? And that's a case where you could hit your reserve sharing group, you could run a negative ACE for a few minutes, whatever you need to do to get through that shortage condition, right? So that's where our kind of extreme shortage hours comes in handy. We've got, we're aligned with the historical context there. So wrapping up, I think I'm gonna be on time. One of the few people that have managed to be on time. I say that, and now I'm gonna eat up 2 minutes. So wrapping up, right? What are we talking about? We've got our operating practices and how those fit into resource adequacy analysis, right? So there's kind of two philosophies that we can talk through. One, we need more and more operational reality into our resource adequacy analysis. What I've proposed here is a secondary type of analysis that leaves the good work of resource adequacy to itself, right? That's its own ball of questions. And we've got a kind of an operating practices strategy or an operating adequacy analysis, which is a little separate, right? Because we've got more system characteristics, we've got more uncertainty, things are different here. The other key thing I wanted to make sure I mention is that our operating reserves are not our planning reserve margin, right? So we all are kind of familiar. Hey, you've got, 15% planning reserve margin. Cool. We'll roll that into hand that to your operators. Life's good. Your operators are going to look at that and be like, 15%. What does that mean? And so we've got to be able to kind of cross that bridge between all this complex stuff that we're talking about for ELCCs and whatnot, and translate that into operating practices. The other key takeaway, right? I tried to downplay it a little bit, but this is around what are we doing with storage, right? And we talk a lot about multi-objective storage dispatch. We know it's capable of providing capacity, flexibility, energy when needed. But that's complicated. It's hard to do on a day-to-day basis. And so the kind of making sure that we're doing that, we're practicing that, we're thinking through, hey, do we need an energy reserve, right? Because we're in an energy constrained system. That's what some of this analysis showed, but I think I want to be careful not to propose that broadly kind of everywhere. So anyway, thank you.
Thank you, Sean. So we go from some operational strategies here to capacity expansion. So our next speaker is Gord Stephen. He's a doctoral candidate in the University of Washington's Department of Electrical and Computer Engineering. His research focuses on the intersection between power system planning and resource adequacy assessment. He also works part-time as a researcher and software developer at NREL's Grid Planning and Analysis Center. He's going to be talking to us today about improving resource adequacy representations in capacity expansion planning.
Thanks, Tom. Let's see if this works. Okay, yeah. Blurry is interesting. Hey, everyone. My goal for the next 15 minutes or so is to hopefully convince some of you, at least, that we can do a lot better than the status quo when it comes to how we internalize resource adequacy representations and considerations and constraints inside capacity expansion models and planning, power system planning problems. I will say that I'm going to focus primarily on variable renewables and energy limited resources, but this is actually follow-up work to some previous project that was looking at endogenizing probabilistic thermal outage risk in resource adequacy and capacity expansion modeling. So if you're interested in thermal risk as well, hit me up after and we can talk about that too. But generally speaking, whether we're talking about renewables or thermal outages, there's this mismatch, right? This kind of impedance mismatch between a capacity expansion modeling process and a resource adequacy assessment. Capacity expansion models, we typically think of as these big, complicated optimization problems that we're putting in lots of constraints and economic considerations into. And as a result of all that complexity and the kind of inherent challenges of solving these big optimization problems, we have to make sacrifices in the resolution or the extent of other parts of the model. And typically the temporal resolution of the model or the number of hours that we can consider in our planning problem is a common area where we have to sacrifice. This is sort of in direct opposition to some of the fundamental tenets of a robust resource adequacy assessment, where we're always talking about how every hour matters and capturing full chronology is super important. And so we have this kind of need to reconcile these conflicting ideas and kind of ways of modeling the world between a capacity expansion process and a resource adequacy check, which is, I would argue, probably the most important constraint that we impose on a capacity expansion model, right? The reason we're expanding capacity is to get to a system that we would consider resource adequate in the future once loads increased or resources have changed. So the fundamental question here is how do we reconcile kind of these two different paradigms? One approach that I think has started to become more common, and we heard a bit about it on Monday. I was actually, I guess it wasn't literally this stage, it was over in the other building, but 5 years ago here at ESEG Tucson Spring, I was up on stage. Tom was on the same panel, actually. I was talking about this idea of iterating between a capacity expansion model and a probabilistic resource adequacy assessment. So you can run your capacity expansion model, you get out kind of an intermediate build plan for what you may be considering as a future portfolio for the system, and then you feed that into a resource adequacy model. and the resource adequacy model will tell you whether your capacity expansion model did a good job or not in designing that adequate system. And it may be that the system was overbuilt and you could actually tone down some of those capacity investments while still meeting your resource adequacy targets, or it may be that the system was underbuilt and you need to build more. And so the kind of traditional feedback mechanism that we have, if we want to iterate between these two approaches, is to adjust that planning reserve margin that Sean was just talking about. So if the system isn't adequate, maybe you need to bump it up from 15% to 18% or 20%, basically force the capacity expansion model to add in more capacity to the system, which you are expecting will improve the resource adequacy of the system. Although the feedback link there between what capacity you add and how the resource adequacy is going to be improved, there's kind of not that much information available to the capacity expansion model. You're kind of just hoping that you're going to get to a point that's resource adequate. This approach still works reasonably well when we're talking about systems with a reasonable amount of thermal generation on them that we're leaning on for resource adequacy purposes. But once we start getting to systems with really high levels of wind and solar and storage and these kind of resources that don't have these nice kind of average availability characteristics that we've traditionally relied on in planning reserve margin analysis, we start running into problems. So in particular, resources like wind and solar and storage all have this really severe issue with diminishing capacity credit, right? The first megawatt of solar that you build on a system might be really effective for reducing the risk associated with serving load in the middle of the day. But you keep adding on that solar, eventually the middle of the day, there's all kinds of surplus, and the riskiest times of the day that you need to be targeting now are maybe in the evening. And you can build as much solar as you want. You're never going to have the sun shining at 10 p.m. at night. So the capacity credit of that storage or that solar, the ability for that building more solar to support serving more load effectively goes to zero. And if all you're doing is turning up your planning reserve margin and forcing the capacity expansion model, which thinks solar has some non-zero capacity credit, you're going to end up with these uneconomical kind of strange investments that don't actually make sense from a resource adequacy perspective, because the capacity expansion model just doesn't have the information it needs to make an efficient investment strategy. So the kind of natural solution to this is to not iterate on planning reserve margins, but to iterate on the capacity credits themselves. So you can make some investments that changes your capacity credits of all your different resources, but you capture that by recalculating all those new capacity credits, or there's some different flavors of this. You could pre-calculate them and then have them in a lookup table or kind of iterate through time. Whatever it is you're doing, you're kind of providing the model with more information about how the system state has changed and how the ability of different resources to contribute to resource adequacy have changed as a result of that. So you can build out your first tranche of resources, calculate a new capacity credit. That new capacity credit then can inform which resources you want to invest in order to improve your ability to carry load or reduce risk on the system. And based on that, you have this kind of more fine-grained, more accurate economic signal that you can use as a basis for a capacity expansion, economic expansion plan. There's still a problem here, though, which is that while we're using better estimates for capacity credits, we're still using capacity credits. And capacity credits are a good kind of stopgap for getting us between this kind of thermal capacity, planning reserve margin based world and a high renewable storage world where we don't really have this idea of dependable capacity. Everything's kind of context sensitive now. But there's a lot more information that a planning model could make use of to make efficient investment decisions beyond just what, on average, typically different resources are going to be able to generate at during shortfall events, whenever those shortfall events may be, right? Ideally, a planning model would be able to know, okay, the thing we're worried about, the source of risk on this system is 2-hour duration events that are at most 300 megawatts deep and happen in the afternoon in July or in the morning in January or whatever the case may be. And with that kind of higher dimensional detail about the actual risks the system are facing, the system or the planning model can make better decisions about which specific resources are best suited to mitigate that particular kind of risk. It's not just about, we need 100 more megawatts. What's the cheapest way to build 100 megawatts? It's when are those megawatts available? What are the energy limitations associated with those megawatts? And what's the cost of all these different options? And what would the most optimal choice of those resources, be it demand response or storage or some kind of dispatchable thermal unit, whatever it is, we can put these all in a level playing field and think about them in terms of how they actually address the specific risks faced to the system, and not just this kind of generic concept of needing additional capacity to meet a planning reserve margin. So I would propose that a way we can capture this information more accurately and more directly in the planning process, and I will say this is all focused on like IRPs and vertically integrated utilities. I don't know what the answer is for capacity markets, would be to iterate on operating periods as opposed to capacity credits or planning reserve margins. So just like before, we can run our capacity expansion model. We can get out an intermediate system that we want to validate. And then we can test that system in a proper, full, chronological, probabilistic resource adequacy model where we're capturing all the hours and all the effects of transmission and storage chronology and all these things. But rather than just getting out a decision of is the system adequate or not, did the model do a good job of building the system, we can actually find out if it's not adequate, when isn't it adequate, and how bad does it get? And once we know that information, we can provide that information back to the model so that it can actually make an informed decision about what resources would be useful in those conditions and plan around those challenges that we're seeing. So I can step through a more concrete example of what that might actually look like using this test system that I developed that's basically a super simplified version of NREL's Reed's model. So it's 134 regions. We're 7 years of wind, solar, and load data, and we're trying to build out as a stress test, kind of a worst case scenario for the capacity credit paradigm. What would it look like to try to design 100% wind solar storage system, given all these transmission constraints and all the kind of tight sensitivities around how investing in one type of resource changes the capacity credit of everything else and in all these different places. So the first step that we can do is pick some starting days that we can provide to the model that are intended to represent sort of the average system operating conditions. So these are kind of your typical representative day period type things. Obviously, these days don't represent the kind of stress conditions that are going to actually cause resource adequacy issues on the system. So we wouldn't expect this initial cut that the capacity expansion model comes up with to be particularly useful in its own right, but it provides us as a starting point. So if we do that, that looks something like this. So yeah, you're nowhere near being able to read these axes, but basically on this side, we have months of the year. And then here we have the 7 different years of the data set, so 2007 through 2013. And then the kind of sub-axis on the Y is the days of week. So basically every box that you see on this plot corresponds to 1 day of this 7-year data set. So there's a little over 2,500 days on here. And of those, we're going to test every single one of them through the resource adequacy model, keeping all the chronology in place, and then see how the system that we build is actually resource adequate or not. And so what we see is a lot of red. I don't have a numerical legend associated with it, but take my word for it that red is bad. Red is a lot of unserved energy. We don't want any red, basically, if we have an adequate system. And as we might expect, the 4 days that we told it about, so there's a spring day or a winter day, a spring day, a summer day, and a fall day. Those 4 days are not enough information for the model to actually plan a resource adequate system. But what we can do as an output of this resource adequacy assessment we've done is say, okay, well, the worst day happens to happen in February 2009. So if the model knew about that day, presumably it could do a better job of designing a resource adequate system. So we can step forward through this iteration process, and this is all fully automated. So the original capacity expansion solve takes about 10 seconds, and then the resource adequacy assessment takes about 30 seconds. Then you can automatically, just programmatically go right back into the next capacity expansion solve, adding in this day in February 2009, as well as the day before. And right away, we see we're starting to improve. We have less unserved energy happening in the summer and winter, although it's still not acceptable. And then a little bit less in the spring and fall. So we can basically just keep stepping through this process and add more and more days. And every time we do that, the adequacy of the system improves. The model has more information to work with about what the sources of stress and risk are and what resources are required to ride through those periods. And as we continue doing this, eventually we get to the point where after we've added in a total of 24 days to the model, it's able to generate a system that's resource adequate across the full data set. So the full 2,500 plus days of test data that we use in the resource adequacy model. So because we've been sort of strategic in discovering and applying the particular risk periods that the planning model needs to know about in order to plan against, we can get away with using less than 1% of the total resource adequacy data to build a system that's adequate across all the other 99% of periods as well. And because this planning model isn't just seeing like average availability during these risk periods, but the actual chronology of what's going on in the system and the detailed kind of hour by hour steps, it can make decisions about being able to deploy different durations of storage, different demand response technologies, other things that you really need kind of that more granular representation of, as opposed to just a kind of a generic capacity number that has a lot of caveats on whether or not you're going to have capacity available in that particular period. Obviously, storage chronology is super important here. In a 100% renewable system, there's a lot of shifting of energy across different days, different weeks, different seasons. And so I won't get into that here. I've got a minute left, but happy to go through the math of how this works and how this doesn't make the size of the problem increase, even though you're representing storage chronology across 7 years, you still only need to represent 24 days worth of decisions and coupling constraints. The other thing I would add is once you've eliminated this idea of capacity credits, you don't have to do some of the things that we've traditionally done to fit storage into a capacity credit world, like treating different durations of storage as totally different technologies. Instead, the model can just say, okay, well, I need this many megawatts and this many megawatt hours of lithium ion batteries or whatever the storage technology is that it's choosing. And then based on that, come up with solutions that are not only lower cost. So this purple is that kind of final result. Not only lower cost because you can size storage exactly to the dimensions you need and not just kind of have these quantized blocks. So it might be like 7 1/4 hours of storage is the right duration for your system. And you're not just trying to make that out of a blend of 6 and 8 or whatever the case is. And it also improves the runtime because now you just have one storage technology in your model and not like 10 for all the different durations that you're trying to capture. So you end up with these systems that are better in terms of the quality of the solution, run faster, eliminate all of the traditional issues associated with capacity credit and interactions with things like transmission congestion and interactions between different types of resources and how capacity credits change, as well as the need to iteratively recompute or pre-compute capacity credits for all of your resources and all the kind of discussions around ELCC versus EFC and which heuristics are appropriate or which you can't get away with. So if this was interesting to you, please do stay in touch. Love to talk about this more. There's my contact information. And thanks for your time.
Thank you, Gord. Our next look at this problem of resource adequacy is coming from Irene Danti. She is a research engineer at the Electric Power Research Institute. She holds a PhD in electrical engineering from UC Dublin. Her research includes resource adequacy, flexibility, renewable energy integration, and demand response. And she's joining us today from France. So please welcome Irene.
Thanks, Rob. All right, is that working now? Yeah. Great. Thanks so much. My name is Irene Danti. I'm joining from EPRI. And so I'm really honored to be presenting here with this great group of people. I was asked to present about transmission and demand side resources and resource adequacy. And I just want to give a disclaimer before I start. These are really exciting topics, but they're also huge areas of research. So I don't know that we'll get to cover everything, but I'd be truly delighted to continue conversations afterwards. So let me just get started here. All right, so transmission networks and demand side resources. Why are they important? Why do we need to think about them when we do power system planning? So they're both key enablers to transition for net zero. They can both provide flexibility, they can both help integrate wind and solar resources, and if planned appropriately, they might avoid the construction of additional fossil power plants. However, in our traditional thinking, they're not necessarily the resources we have given the most attention to when planning. especially from a capacity expansion and resource adequacy perspective. So many people are doing many different things for thinking about demand side flexibility and transmission planning. And there is a lack of a clear framework when you start thinking about a consistent way of integrating this into power system planning, that the framework just isn't there. So demand flexibility, for example, is not often modeled in a lot of detail in resource adequacy. And it's still considered as an emergency procedure and not something that you'd use in day-to-day operations to support power system operations. And that might trickle down from the fact that at the planning level, it's not really considered that well. So let me start talking about demand side resources and resource adequacy. And I will say that when we started looking at this topic, one of the key questions that came up is, what is a demand side resource? What is demand flexibility? And so I'll go into that to start off this discussion. We've been thinking about this a lot, and we've come up with a framework and some wording to give us some vocabulary to think about demand flexibility. So we came up with this definition: demand side flexibility is any adjustment in the customer net load that is measured at the customer meter and that is enabled by programs that trigger response from demand side resources. So when we think about demand flexibility, we also need to think about timelines. When is your unit responding? And that's going to affect how we plan. So building on existing work, this is the kind of timeline framework we've come up with. We have that shape response that would characterize any long-term behavioral change from things such as energy efficiency. And then we have the shorter term responses, which we're calling here flex and shift, but I know there's other terminology out there. And I just want to give a shout out to the LNBL colleagues here, because I think they did an awesome job of starting this discussion. Flex and shift are shorter term. They're used to mitigate routes. They're used to capture surplus generation. They're used to manage contingency events. And a lot of the gaps we have in modeling demand side flexibility and power system planning are actually here in the shift and flex level. So the difference between the two of them is that shifting involves an energy payback. So you ask a resource to reduce consumption or to increase consumption, and that resource needs to make up for that later on, like a smart thermostat or like an electric vehicle. Flex just involves a customer that will reduce or increase and does not that doesn't change. There's no need for an energy payback later on. Demand side resources. So in the past, we've mainly thought about flexible demand being the main demand side resource. But I will say that with advanced net energy metering programs, distributed generation, I think, is also very much worth considering as a demand side resource, and distributed storage. So this is another definition we came up with. Demand side resources would include load, customer located generation, and any other customer located technology that has the capability to provide a response in response to a signal. Okay, so I'll give a quick overview of some work we've been doing. We've been trying to understand how distributed resources and demand side flexibility can support resource adequacy. And we're trying to understand how to develop models that accurately capture their behavior, and not just their value, but also their limitations. Because if we want to plan power systems that are reliable, if we want to essentially take demand side flexibility seriously, we need to understand how it performs, where it performs well, and then what the limitations are. And the limitations are really important. So we've looked at all those resources that are in green there. We're looking at smart thermostats under reliability dispatch, industrial commercial loads that are subject to real-time prices, users on time of use tariffs, electric vehicles charging on time of use tariffs. And we've also been looking at a couple of combinations of distributed PV and storage coupled to different tariffs. incentivizing how they behave. So whether they're exporting, whether they're not exporting, and when they're exporting. This is a very quick summary of some of the results. And the key message here is that these technologies can help a lot. So the vertical axis on that graph, it's a plot of the loss of load expectation, LOLE. We generally plan for 1 in 10 days of lost load. That's the kind of industry standard. And that's what we see in the gray bar there. That's the base case. And this plot shows how LOLE was affected when existing demand was shifted to be flexible. So it was shifted to be responsive to time of use tariffs, or shifted to be responsive to real-time tariffs, or shifted to become smart thermostats that respond to reliability dispatch. And this is for a 3% of peak demand rollout. This was a 30 gigawatt system, and this is a 900 megawatt rollout. I will say though that lower rollouts already made a difference. We looked at 1% and it already made a difference. And so I think this is very encouraging. It's very positive to see this happening. So there's differences between how programs react. For example, time of use tariffs have a lower impact on LOLE. And the reason behind that is mainly that every megawatt that's subscribed to a time of use tariff, we'll only have about 10% that's flexible. For price responsive demand, it's about 30%. And then smart thermostats, it's somewhere between 70 and 90% of the load there. Distributed PV performs really great in this system because it's a system that does not have a lot of solar at the moment, but it is a summer peaking system with a peak load happening at midday during the summer. So yeah, any solar on the system helps. So as I said, these initial results are really encouraging, and they're really making us question how to understand these resources better and what else we can do to help the industry think about them and model them. And I think the main issue we're having is here. So this graph shows, let me see. This we have on the right side, the supply side, and on the left side, we have the demand side. And so we're looking at how supply side models, right? Let's take the right side. We have a standard way of thinking about thermal models, wind and solar models, hydroelectric models, energy storage. I think for most people in the room, if you were asked to model a gas plant, many people would think, okay, there's PMIN and PMAX I think I need to think about. I need to think about ramping constraints. I need to think about startup times. And then once that is more clear, there's some other additional features to think about, such as what kind of markets are they going to participate in? Is it energy only? Is it going to provide reserves? And then some cost information. And so the framework is there. We all share this common knowledge. When you think about the demand side, however, there are still a lot of questions. So we've been trying to put the framework together. We're thinking about dividing the demand side into 3 separate categories. We have the firm load, the load that is not going to respond to any short-term signals. And that's always been modeled as time series, and it should probably be continued to model as an exogenous time series, and that's great. However, when you think about these flexible and shiftable loads that do have the capability of responding to real-time price signals or real-time dispatch signals, we do need to think about what constraints we need to add there. And there are a lot of gaps there still. We know that there's a time varying Pmax there that might vary by season, or it might vary by hour of the day. We know there's some sort of limit on the number of times we can call upon units. There's some sort of limit on the energy we can ask for units to provide. And then there's a whole range of other constraints that we don't know that much about. Customer fatigue is rarely modeled, but it can be crucial, very important to understand if we're going to plan systems of demand side flexibility. The weather dependency of demand response is also crucially important because people might be okay turning down their thermostats under a regular day. What happens if it's an extreme heat day or extreme cold day? Are we going to get the same level of response? And then the biggest gaps we have found in this work is this shiftable load modeling. And shiftable loads are electric vehicles, they're smart thermostats, or electric water heaters. They're the loads that are really growing today. So it's really important to understand these loads. And we need to understand how far we can defer energy payback, whether there's a compounding rate or whether energy shifting always adds up to zero. So a lot of questions, really exciting area of research, and we're thinking a lot about this. To close on the demand side of things, I will also say that I usually have a resource adequacy hat on, but there's a lot of other things going on in power systems, and they're all linked. And this brings me back to the integrated system planning tutorial on Monday, which I thought was fantastic. And I thought it was just great that we're talking about that. There's capacity expansion, there's transmission planning, distribution planning, and I'm probably not even covering everything that goes on in planning there. But if we're trying to think about how to include demand side response into power systems and how to reliably plan power systems with demand side response, we need to think about these other areas as well. And we need to think about whether uses in distribution planning might be actually contradictory to what we want demand response to be doing in resource adequacy or transmission planning. So we've started thinking about this as well. And so this is a really exciting area of research. And I will quickly cover transmission constraints. So transmission constraints, and very much like demand response, there's just a lack of a standard framework. So when we see resource adequacy results, it's rare to have in mind all of the assumptions that have been made in transmission modeling. And what we're seeing in our work, and I'll show some slides from the work we've been doing now, is that it really does matter a lot. Those assumptions matter a lot, but again, we don't have a framework in mind to think about this. We don't have a list of the key questions to have in mind when looking at results on how can our assumptions around transmission constraints, how may they have impacted the results that we're seeing from adequacy studies. And so this is a slide from some very interesting work we've been conducting with our colleagues in Astrapi Consulting. This work, what this slide shows is that there's not just one way of thinking about unserved energy when we model transmission constraints differently. So we generally have that copper sheet assumption. It's very common to take that assumption in RA when we model constraints within a region. And so what that graph at the bottom shows, for example, it says option 1 in blue when we have the copper sheet assumption, which is option 1 outlined above there. We're distributing loss of load essentially equally across every area that we're modeling, even though that might be very far from reality. When we start considering transmission constraints, and that's option 2, the way you assign expected unserved energy, or the way that you lose load, is going to be proportional to how much generation you have locally, and transmission constraints will affect it very much. So option 2 there shows that when we start thinking about transmission constraints, we start seeing that zone 1 actually has a significant generation deficit. Zone 2 does not, and so it doesn't affect zone 3 here so much. And so I think that the key takeaway here, the overall point that I would like to make, is that this is not something we keep in mind so much. Different folks do different things. And we do think there's a strong need for a framework and just some guidelines to be able to think about these problems and some wording. And sometimes it's a question of vocabulary so that we can talk to each other and understand what others are doing a bit better. So I'm out of time. I will stop there, but there's my email, and I would really love to continue discussions on this topic if anyone is interested. Yeah, thank you.
Thank you very much. So transmission, getting resources from our neighbors. One way we get resources is through markets. And so we have Leah Kaffine today. She spent the past 15 years in quantitative roles in the energy industry, including utilities, a national lab, energy software, and consulting companies. Currently, she leads a team at Pattern Energy as the director of fundamentals. Her team's deep understanding of electricity and other commodities markets enables cross-functional finance, origination, trading, policy, and construction efforts across Pattern Energy. She holds a BS in applied mathematics and a BA in art history, both from UC Santa Barbara, and works remotely from her home in Golden, Colorado. She's going to talk to us today about resource adequacy reform, uncertain heterogeneous markets. Thank you.
Hello. Oh, it was loud. Okay. Better too loud than too soft. Okay. Hi, it's great to see you all here today. So many friendly faces in the crowd. So thank you for having me part of the panel. Debbie, thanks for the invite. I'm going to offer a little bit different perspective here today from the standpoint of a developer, owner, operator of wind, solar, and transmission. That's Pattern Energy. Our portfolio includes 15 gigawatts of wind and solar. We are exclusively green company, so a little bit different. We have 1,100 miles of transmission operating and in development. That includes SunZia, which is 550 miles of transmission from New Mexico to Arizona for the SunZia wind project, north and south SunZia. So a little bit about Pattern. A lot of people ask me, who's Pattern? So that's who they are. Fantastic company with a great mission. And I'm very excited to be a part of their team. So I'm going to just kind of go through, kind of how I've been looking at markets for Pattern. And I was going to, it's maybe it's a little late for an analogy, but I'm going to do it anyway. So I heard this analogy, I really liked it. Like, so a capacity, like resource adequacy is basically having the car sitting outside waiting for you, right? Just sitting there. The energy is when you actually get in and use it. They take the car to the airport, right? So, sometimes you want an EV, right? You have a preference for that car to be green, or you have, some sort of special circumstances where you need that car to be something different. Maybe it needs to be some sort of armored vehicle to get you to where you're going because of whatever's happening that day. Or a hovercraft or something like that. So kind of just like to have that analogy because, even in some PUC meetings that I'm in, there's kind of this misunderstanding of what resource adequacy is. It's to have it there for when it's needed. And then I'm going to kind of talk through capacity markets because I'm obviously very revenue focused in my role. And, the way we think about capacity markets is the missing money for new and existing generators to be available when needed. So payments to generators to make sure that they're there for the adequacy needs on the system. Usually out looking like a year, the next 2 years, 3 years, which, is that long enough? So what makes this hard? Capacity markets have been around for a while, but what's making it difficult now, which is why we see so much change going on, is obviously intermittent resources, the climate interdependency between load and generation, retirements almost happening like too quickly. As much as we love to see, some of these generators retire, it does cause some problems on the system. So there's considerations on, how long do we really need to keep them on as providing resource adequacy. It gets difficult when you have a single price signal, but you have all these different objectives, right? Like there's like a lot of things you want to kind of make happen through the capacity market, but really you're just sending a single price signal. We'll kind of get into like the different bifurcations that are happening. So people have varying decarbonization goals within these capacity market footprints, right? Like each load serving entity can have kind of a different goal, and even across the footprints, imports and the demand response are all kind of considered differently. So that can make it's also very difficult to implement any kind of change in these markets. There's a lot of stakeholders, there's a lot of competing interests, and it's about spending money really, and spending ratepayers' money, and it can be very difficult to get changes into these markets. So it's always kind of even if you have a great solution, communicating that to all the stakeholders and getting everyone on board can be very, very difficult through regulatory proceedings. So these are kind of the buckets that I've been thinking of capacity markets when someone brings a project to me and says, can you please understand what kind of capacity payments we can expect for this project? A lot of stuff we're doing out west is bilateral. So there's like a defined sort of obligation for the LSEs. There's no kind of like clearing auction. The prices are negotiated, right? And a lot of times it's bundled energy, REC, RA, and that creates kind of transparency issues for price formation. Like it's not transparent. So that's actually how most of MISO actually works also. And so it's just that's one kind of like bucket that's kind of happening for resource adequacy. And then there's the clearing markets, the very highly structured auctions, PJM, ISO New England, the rest of MISO kind of clears that way. And then you have these emerging markets, which are not price markets, like there's no price signals within these markets. It's just a compliance in RAP and SEAM, and underneath that are a bunch of bilateral contracts, basically. And then the last one is energy price modifiers, or the ERCOT ORDC. And just when I think I've heard it all, there's Alberta economic withholding, which is a feature of the Alberta market. It is also an energy only market, and they use economic withholding to ensure that resources can stay online to provide resource adequacy. So it's all very different, which can be tough. So you get this difference across markets, right? The market designs are all very different. And then within that, there's this difference, and this has been talked about earlier in some of the other presentations, is the resource counting and accreditation capacity credits. There's a lot of different methodologies for kind of calculating these. There's this desire to have an accreditation method that's technology agnostic so that everyone's treated fairly and it's all equal. But that's very difficult when you also need to have a generation mix that can provide a reliable mix. So when everyone's kind of competing on an even playing field, you don't necessarily get a portfolio mix that has the diversity that you really need on the system in order for it to be, providing everything that you need at the time that you need it. So there's been some efforts, and this is from the CPUC, which is again where I've been most involved because of SunZia, where they've been looking at redefining, instead of using an ELCC, moving to like an exceedance or a slice of day kind of metric instead. And this just kind of shows you for the same resource how they will actually count the nameplate capacity differently across those different kind of proposed methodologies that they have. And some of them focus on, the hours of concern. We kind of talked about the hours of concern, which right now are hours 16 through 21. Those kind of shift to later in the day as you get more batteries on the system. So your hours of concern can actually move and change over time. There's this kind of issue of like picking a certain slice and saying that's the slice we care about, when that can really change. So, and again, you can see how much it varies, depending on these kind of changes. So, making sure that, so I think like resource counting is the place, where they're going to say like, this is what we need to change something here in order to get the mix that we want, and not just have everyone be on an even playing field and then everyone just builds a shit ton of the cheapest thing, which is solar, and then you have to so you end up with other problems on your system. So you're trying to make like these like modifications to the existing market because it's easier to get those through, right? In this regulatory environment, it's easier to just make adjustments to the existing kind of systems that these markets have, instead of like doing a full redesign and saying we need something completely different. So that's why you see, the slice of day, you see like seasonal markets coming up, and then marginal ELCC are all kind of like efforts to create kind of steps in the right direction, so that other markets are looking at what's happening in California and saying, hey, we don't want that to happen here. We want to be a little bit more thoughtful about what's coming on our system, and just not have it be a free-for-all. So, okay, I'm actually probably moving really fast, but that's okay because you guys, this is lunch coming up. I get that. So this is the hardest part, is that when you have this much uncertainty in the market with all these different reforms going on across all the different markets and changing resource counting and changing market structures, it's so uncertain. Like people ask me, what's our revenue going to be 10, 20 years from now for this project for capacity? And I was like, I can't tell you what it's going to be a month from now. Like things are changing so rapidly. These are articles, like one's from 5 days. This is just like the past month, these headlines. This is just drives me crazy. So it's very difficult for banks to be able, for me to convince a bank that, this revenue will be there and it will be realized. Because who knows what the future market will look like. The benefit to the bilateral kind of negotiations that I talked about before is that it's contracted and it's certain. So there is that, but there is, again, no kind of price transparency. It does allow LCs to be like very targeted in their procurement. So they'll put out very specific RFPs and like they can say, this is what we want our resource mix to be, and these are our goals, and we're going to go out and get exactly what we need. So it's very target based, as opposed to a competitive market. So there's some benefits there for project financing, which is getting more difficult. As great as IRA has done a lot of great things, one of the things, one of the consequences of it also is that there's less tax equity available in the market, which is very, very important for project financing. And then capital construction costs are up. I think everyone's just kind of aware of all the cost increases going on around the market. So those are challenges. So you just have more missing money for projects, right? Which you can't really look to capacity markets to make up, where RECs exist. Again, there's also a patchwork quilt of RECs. So you have energy, you have RECs, and you have capacity, and they're all kind of different layers of a cake that's not really connected at all. So it's really a lot of effort, like every time you look at a project to try and understand, how the revenue streams are gonna really form in the future. So that's my challenge. And it's great that we have all this research, and I encourage people to be active in all these RA reform. I know Telos is and others are active in sort of the RA reform tracks, which is really great to lend knowledge to those working groups as well. So that's all I have. Thank you.